Welcome to the video about conjugate addition. This is found in chapter 21. For this reaction, we need to have an alpha beta unsaturated ketone or aldehyde. So the alpha carbon is the first one away from a carbonyl, the beta is the second one away. We will learn in organic 2 that we can use an aldol condensation to take a ketone or aldehyde into an alpha beta unsaturated ketone or aldehyde. But for this reaction, we need a double bond right next to the carbonyl. If we look at that unsaturated carbonyl, we can see that it has 3 resonance structures. One placing the positive charge at the carbonyl, which is what we're familiar with and comfortable with to this point. An additional resonance structure, however, puts the positive charge or the electrophilic site at the beta carbon. And so this is what we'll be talking about in this section. So if we look at those resonance structures, we see that we have an electrophilic site here at the beta and also here at the carbonyl position. Both can be electrophilic sites when we have a good nucleophile. And so let's talk about how we're going to have the reactions happen preferentially at either of those sites. A Grignard reagent is going to typically happen at the carbonyl carbon, shown right here. So our negative carbon nucleophile is going to add directly to the carbonyl carbon because it is a strong, good nucleophile. It turns out that the weaker organometallic reaction, the Gilman reagent, preferentially adds to the beta position. This carbon is negatively charged, but it's not as strong of a nucleophile as the Grignard. So the stronger the nucleophile, the more likely they are to react at the carbonyl. The weaker the nucleophile, the more likely they are to attack the beta position. And so the mechanism for this reaction, we have a nucleophile that's going to take the lone pair and create a new single bond to this carbon right here. In response, the pi bond electrons are going to hop over. In return, the pi bond of the carbonyl is going to hop up. And so we end up with this enolate intermediate where our nucleophile is now covalently attached. So following the nucleophilic attack, we're going to have proton transfer where that negatively charged oxygen is going to be protonated. And so we end up forming the enol. Enol comes from the term that we have an alkene next to an alcohol. That enol quickly tautomerizes into the ketone or aldehyde. This is not exactly a resonance structure. It has a term that's called a tautomer. Anytime we have an alcohol that's on a double bond, we can form this tautomer or have this tautomerization reaction where the proton that was on the oxygen becomes attached to the carbon and we form the ketone or aldehyde. So our final product is that we've added a nucleophile to the beta position of our ketone or aldehyde. And this is actually called the 1,4 addition. Stronger nucleophiles tend to add right to the carbonyl, and we'll call that a 1,2 addition. Less reactive nucleophiles give the conjugate addition, which is what we call the 1,4 addition. Typical enolates often give a mixture of 1,2 and 1,4, and anything that can have a stabilized enolate, that intermediate, will give the 1,4 addition exclusively. So a very typical conjugate addition or 1,4 addition is called the Michael addition, and this is where we end up thinking about having a Michael donor, which is the nucleophile that does the best conjugate addition. And then we have the Michael acceptor, which is the alpha beta unsaturated carbonyl. We put those two together to have this Michael reaction. Here's a table showing some common Michael donors and Michael acceptors. So here on the left-hand side are things that can work as the nucleophile for the 1,4 addition. And then over here on the right are the ketones, aldehydes, and other species that can act as our alpha beta unsaturated. And notice here that the beta position is highlighted in all cases. So a second important conjugate addition reaction is the Stork enamine synthesis. In this case, we take a ketone or aldehyde and we'll react it with a secondary amine. Recall in the previous chapter how we took a ketone or aldehyde and reacted it with a secondary amine to afford our enamine. If we look at that intermediate, the enolate intermediate that we want to be stable in this conjugate addition reaction, we have a resonance structure which puts the negative charge right on that alpha carbon. And it turns out when we have an enamine, we can actually do the same thing. When we have our enamine, we're going to have a resonance structure that puts the negative charge right on the alpha carbon. This enamine is a Michael donor. So the enamine is going to be the nucleophile that attacks the beta position, kicks over and kicks up, and then we protonate. And then we have the tautomerization. And then after the conjugate addition, we have an aqueous acid workup which converts both groups into carbonyl groups. We protonate and then we have the tautomerization. And so if we think about the overall process, it's a 3-step reaction. First of all, we form the enamine using these reagents right here. Secondly, that's going to act as a nucleophile, and we're going to do Michael addition to our alpha beta unsaturated ketone here, and then we're going to work up with acid to end up with our diketone product. And if we do a quick review of the 2 reactions in this part of the chapter, Michael addition and the Stork enamine synthesis. Okay, good luck.